Greetings everyone. I am Manasa KM bearing the USN 1VE 19CV012. I'm going to give a seminar presentation on submerged floating tunnels under the guidance of Mr. KM Chaitanya, Assistant Professor, Department of Civil Engineering, Sri Venkateshwara College of Engineering, Bengaluru. Going to the introduction part of the seminar, what is a submerged floating tunnel? A submerged floating tunnel, also known as a suspended tunnel or Archimedes bridge, is a proposed design for a tunnel that floats in water and is supported by buoyancy. Submerged floating tunnels were first envisioned in the early 20th century, but there are no projects that are started until lately. Submerged floating tunnels can cross deep or large waterways. These tunnels float below the water surface and are anchored to the seabed, making them stable and weather resistant. The objectives of a submerged floating tunnels are they can speed up and simplify transportation between two areas, that is, large areas separated by water. This improves the transportation system and helps save travel time and make transportation easier. Decrease environmental impact. By eliminating bridges and causeways, surface ferry terminals can reduce the environmental impact of transportation. They may be more cost effective than conventional infrastructure such as bridges or tunnels, which may need extensive evacuation and constructing. Aesthetic appeal. They can be built to integrate into the landscape and minimize their impact. They could improve the landscape's attractiveness. There were some papers which were found based on this topic. First one is the Submerged Floating Tunnels by the authors T. Aarti and G. Murugeshwari. In this paper, the overview and the introduction and a few other details about submerged floating tunnels were found. What was found is that SFTs are an innovative infrastructure solution for crossing large bodies of water. They have a number of advantages, including lower environmental impact, increased safety, and faster construction time. They also do face a number of challenges, including hydrodynamic and structural issues, as well as environmental concerns such as disruption of marine life. Advanced materials and construction techniques, as well as use of simulation and modeling tools, are potential solutions to these challenges. SFTs have been proposed for a number of global projects, including the Norway Denmark link and the Tokyo Bay Aqualine in Japan. These case studies demonstrate SFT technology's viability and potential. Continuous research and development is required to advance the technology and address the challenges. They have the potential to provide significant economic and social benefits such as increased connectivity and reduced travel time. They can also benefit the environment by lowering the carbon footprint associated with traditional transportation infrastructure. The next paper which was found is Challenge in Design and Construction of Submerged Floating Tunnel and State of Art. This research looks at the difficulties in designing and building submerged floating tunnels. The authors investigate the cutting edge technologies used in such tunnels. They are a newer type of tunnel that presents unique design and construction challenges. The main challenge is keeping the tunnel stable in the underwater environment. The authors go over the various types of submerged floating tunnel designs, such as suspension, semi submerged, and fully submerged tunnels. They also investigate the materials and construction methods used in the tunnel's construction, such as prefabrication and modular construction. The study emphasizes the significance of precise and detailed computer simulations and testing during the design process. To ensure the tunnel's safety and durability, the authors emphasize the importance of strict quality control during the construction process. It looks at the potential advantages of SFTs and such as reduced construction time and cost. While there are challenges in designing and building SFTs, the authors conclude that they are that they offer a promising solution for coastal transportation infrastructure development. The next paper which was found is feasibility study on the submerged floating tunnel in Qingzhou Strait, China. The study looked into the viability of a submerged floating tunnel in China's Qingzhou Strait. The authors investigated the area's geological, meteorological, and oceanographic conditions. The strait connects the island of Hainan to the mainland of China and is located in southern China. The proposed distance is 3.8 kilometers. The precast concrete segments of the tunnel would be anchored to the seabed. Given the favorable conditions in the area, the authors concluded that the proposed tunnel could be feasible. Conditions that are favorable include relatively shallow water depth, moderate wave and wind conditions, and a stable seabed. The tunnel would provide an alternate route between Henan and the mainland, reducing travel time and distance. The authors state that additional research is required to determine the economic and environmental impacts of the proposed tunnel. The study adds to ongoing debates about transportation infrastructure development in China, particularly in South. Moving on, to the utilization or uses of submerged floating tunnels. The SFTs provide a direct and efficient transit route between two land masses separated by sea. They can be used to transport water, oil, gas, and other liquids across waterways. SFTs can handle tidal, wave, and wind energy. They can sustain offshore wind and underwater turbines. SFTs can support telecommunication infrastructure and aquaculture as well. Methodology. The operation of a SFT involves the provision of a channel below the surface of a body of water. It can float on water due to buoyancy. Air-filled pontoons across the sea-floor tunnel keep it afloat. Anchorage. Cables and other anchorage methods secure the SFT to the bottom. Water forces, including waves, tides, and currents, must be able to withstand the anchorage system. Submersion occurs after the SFT is secured. To provide ventilation and access, the tunnel is usually partially buried. Tunnels may be submerged as well. Transportation. The routine maintenance ensures SFT structural integrity and occupant safety. Maintenance includes inspecting, repairing, and cleaning tunnel and anchoring systems. There are some general steps which are involved in the process of building an submerged floating tunnel. The first is the feasibility study. A feasibility study evaluates a project's potential by considering site conditions, environmental impact, economic variables, and technological feasibility. If the feasibility assessment confirms the project can be completed, the design process begins. This requires a precise design that accounts for water depth, seabed characteristics, tidal currents, wave action, wind forces, and other environmental factors. Materials must be carefully chosen to withstand harsh maritime conditions. SFT materials are similar. SFT buoyancy, stability, and structural integrity can also be affected by its building materials. They are built by manufacturing tunnel sections and towing them to the assembly site. After the SFT parts are assembled, they are lowered into the sea and fastened in place. Design and site constraints affect installation. Testing and commissioning. After installation, the SFT will be tested and commissioned to ensure safety, stability, and performance. The materials required for construction of SFT are steel, and they often use concrete, composites such as fiber reinforced polymers. Composites make a great SFT due to their low weight, high strength, and corrosion resistance. They are used to build tunnel hulls and other structural sections. Plastic. SFTs may be made from plastics like HDPE, Plastic is lighter and more corrosion resistant than steel or concrete. The principles of SFT. SFTs float on water. The tunnel's static behavior and dynamic response depend on buoyancy and self-weight. Minimum internal dimension and near optimal design are strongly correlated. SFTs can be floated in two ways: positive buoyancy and a negative buoyancy. Positive buoyancy occurs when the SFT is anchored to the sea floor by tension legs or pontoons. The negative buoyancy is one in which a structure would have piers or columns extending into the water for foundations. This method works only in 100-meter deep water. Waves, currents, earthquakes, corrosion, ice, marine growth, and water related environmental events can damage SFT. It should be built to withstand all such activities, including operational and accidental loads. Bottom anchoring increases the transverse rigidity of the SFT. Moving on to the structural components of a SFT. There are three fundamental components of the SFT, which are tube, anchoring, and shore connections. Tube. As you can see in the picture, this shows the picture of a tube. It should have enough room for the equipment as well as the traffic lanes. External form might be round, elliptical, or polygonal. It's possible that it's made out of concrete or steel. Protection against corrosion is the primary concern of the construction of a tube. The length of the individual parts that make up the tube might range anywhere from 100 meters to 50 meters. Next is the anchoring. There are basically four types of anchoring. First one is the SFT with pontoons. This type of uh, anchoring is unaffected by the water depth. Nonetheless, the system is susceptible to wind, waves, current, and the possibility of ships colliding with one another. The construction needs to be designed in such a way that it can continue functioning even if one of the pontoons is destroyed. Next type is the SFT supported on columns. It is an underwater bridge with foundations on the bottom, and although the columns are in theory in compression, there is also the possibility that they may be in the tension. The depth of the water will play a crucial part in this scenario, and at the moment, a few hundred meters is regarded to be the limit in terms of water depth. However, investigations into far deeper foundations are now being done. The next type is SFT with tethers attached to the base. It is predicated on the tethers being under tension in all potential future scenarios, and there is to be no slack in these tethers tolerated in any potential future load instances. Whether the tethers are vertical or a mix of vertical and inclined, the current practical depths for this form of crossing may be several hundred meters deep. This is true regardless of the orientation of the tethers. The next type is SFT unanchored. It is fascinating since it does not have any anchoring at all, except for when it is on landfalls, and it is then independent of depth. There is certainly a limit to the length, but the solution to this question can only be found by future development. It is possible that an alternate route for light traffic, maybe one that is 100 or 200 meters long, should be constructed. The next component of SFT is the connections. The shore connections of the flexible water tube need interface parts to correctly connect it to the stiff tunnel built in the ground. This joint should inhibit tube movement without producing long-term strains. Nevertheless, airtight and watertight joints prevent water from entering. In seismically active areas, shore connections must be made with caution due to undersea landslides. The competitive features of SFT are invisible since it is built under the level of water. The length only ranges from shore to shore. It is very low gradient. It may surface just above the shoreline. It is built from highly it is built far from highly populated areas. Simple removal at the product's end of life, as the component parts are recast and are towed to the site and then assembled. Some opportunities for reusing or recycling materials, that is, the building materials used in SFT. Applications of SFT are deep water crossings, transportation of oil, gas, or water over underwater channels. They have they serve two purposes. They protect the pipes and make it simpler to maintain and repair them. They also help for transporting data cables for internet and telecommunication networks. The turbines and generators that make up hydroelectric power plants may be housed in SFTs if the plant is of supercritical design. They can also be used as docking stations for submarines and other underwater boats, and they can be used for aquaculture farms. Moving on to the advantages and disadvantages of SFTs. Advantages are they can be placed in areas where traditional bridges and tunnels are impractical. This gives placement flexibility. Next is for deep water crossings with intermediate support structures, they may be cheaper than bridge or tunnel construction. This is especially true compared to tunnel construction costs. They have lower environmental impact compared to conventional bridges and tunnels. They can be built off site and floated into place, which reduces the construction time in half. This reduces construction time and environmental impact. They are durable and secure in stormy ocean conditions. There are, however, a few disadvantages to SFTs as well, such as they have high construction costs in some cases, they require significant engineering for stability and safety, limited access. SFTs may have a smaller environmental impact than bridges or tunnels, but they may still harm marine ecosystems and habitats during construction and installation time. SFTs may block shipping channels or other waterways depending on their placement and arrangement. They may not be ideal for high traffic transportation routes. There are a few case studies for SFTs. The first is the Rockfast Tunnel project. It is a notable SFT case study. It will be a part of Norway's western coast E39 coastal route, which connects several major cities and villages. It is the world's longest and deepest undersea tunnel, which will be 27 kilometers long and 392 meters deep when completed. It will have a 3.7-kilometer SFT. After being built elsewhere, the tunnels will be floated to their destination and fastened to the bottom with cables and pontoons. It will happen off site. The pontoons will be filled with water to keep the tunnels underwater, but cables will hold them in place to withstand waves and currents. The project has faced many challenges, including high construction cost and the need to ensure tunnel safety and stability in harsh ocean conditions. The project used cutting edge engineering and construction methods to overcome these challenges. Innovative materials and computer modeling are used to simulate tunnel behavior in various environmental conditions. The Rogfast Tunnel project is expected to reduce travel times and improve coastal city and village connections in Norway. The project should benefit the economy and environment. It will eliminate long, fuel intensive ferry rides and provide a more environmentally friendly transit option for locals and tourists. The next type of tunnel which was planned is the transatlantic tunnel. It is proposed underwater floating tube connecting North America and Europe across the Atlantic Ocean. 54,000 prefabricated components linked by watertight and vacuum-tight gaskets would build the transatlantic tunnel. Tethers will connect each tunnel segment to an anchor at the bottom of the sea, which will be about 8,000 meters deep in some locations. The tunnel would waver under pressure to avoid ships and reduce pressure. The tunnel would be 45 meters below water, and high speed rail may take 54 minutes from New York to London. Yet the railway would need to move at 8,000 kilometers per hour through a 5,000-kilometer floating tunnel in the Atlantic Ocean. To reach this speed, the tunnel would need to be practically vacuumed and the train magnetically levitated. Three rails, three are unidirectional, and one is a reserve for emergency or maintenance. Conclusion: the submerged floating tube will be open to new avenues for advancements in transportation engineering, which will be reflected in the quickening pace of technological developments that reduce travel time. While preserving the natural beauty of the landscape, moving the vehicles below the water surface will improve the transportation system and free up valuable space for new uses. There are potential benefits from using less energy as well as from producing less noise and air pollution. A SFT will gradually replace ferries, giving local communities new opportunities for improved connectivity and regional development. In doing so, deeper and wider crossings will be possible. These are the few references for this topic. Thank you.